All right, so what I have here for you is a last prompt, and I just simply want you to find the error that the student made in this case. We have two students, one is Russell's and the other one's Consuela. They're trying to prove whether or not these two triangles are similar. Okay, now if you don't understand what similarity means, we'll talk about that in a minute. And you want to determine whether Russell is correct or Consuela is correct. Any idea at this point in time? Just by looking at it? Okay, if you have no clue whatsoever, don't worry about it. I'm going to talk about the lessons first, and then we'll come back and prove this once and for all to see who is correct and who's not. Okay, so let's move on. Okay, so this is our theme for today. Look here. Ooh, have you ever heard of the Lamborghini Veneno?
No.
No. Oh my God. It's a $4 million car.
Very rich.
Oh, apparently. And
You have
they,
one?
no, I don't. look, read my second sentence.
Because I'll give it to replicants.
Too expensive. I think only about 4 are made in the world. Only 4 or so. It's not mass produced or anything like that. It's very special. You know how it is. And so, very fast car, simple car. It's a nice car. But
How many seats is it?
2.
What the heck? Oh, that's so big.
That's so
Isn't
nice.
it mini?
Very nice.
That's why these guys are better.
It's okay. It's okay.
You're so amazing, man.
Anyway, but the key here is this. Notice how I said, here's the real deal. And I said, no, it's too expensive. I'll get a replica instead. Now, what does it mean to say I'm going to have a replica? A fake one, but
Looks like it.
okay, wait, say it again.
It looks like it.
It looks like it. So can we say what I have is similar to the actual original?
Yeah.
Similar. Notice I'm using the word similar. That means if I just look at the replica, or in this case the toys one, the toys version of it, I don't think it's going to be as big, right? The toy replica is going to be a smaller version of it, but if I look at the details on the design of the car, it should have all of the similar features. Is that true? Notice I'm using the word similar again. So based on that, when I say something is similar, what do you expect to see?
Not exactly the same.
It looks exactly the same.
It looks the same, but small.
It looks the
Okay,
same, but what?
It's
Smaller.
or
It's smaller. So can we just conclude that when I say something similar, they have the same shape, but not the same size? Is that fair enough? Just like how I have these two triangles right here. Notice I have a big triangle here and a smaller one, and clearly you see that they are similar. They have the same shapes, but apparently not the same size. Is that true?
Mm-hmm.
Same thing for these two. Same shape, but not the same size. Okay? Now, so that's what similarity means. What about congruent? Have you ever heard of the congruent before?
Same.
When I say something of congruent, what does it mean?
Same shape.
Same shape, same size.
Same shape and same size. Very good. So they are exact copy of it. So when I say something's congruent, they must have the same shape and same exact size. So the difference between a similar figure and congruent figures are similar means same shape but not size, but congruent means same shape and same size. So if you look at this carefully enough, let's think about this for a moment. We need to learn a way to prove similarities. So how do we actually prove it? We have 2 ways to prove it. Now I'm going to go ahead and write this down right here. You want to jot this down. Okay, so we have to prove similarities. Kind of, oh my God. Okay. You can do one of 2 things. Okay, either all interiors angles are the same, that's the first thing. All interior angles are the same. If they are all the same, we are guaranteed to have similar figures. For example, look at this first case. You see these 2 triangles? Right now, I do not know whether they are similar or not. But if I start calling this, well, here you go, guys. If this is 60 degrees, if this is 60 degrees, what do you think the third angle is going to be? Why? Okay, so you know that the sum of all three angles on a triangle has to add up to 180 degrees. So that has to be 60 degrees as well. So that's pretty much given. You know that. This triangle right here, what if I say, oh yeah, I know this is 60 degrees and this is 60, then what's the other one has to be? 60 degrees. Okay, so in this case, when I have all interior angle or corresponding interior angles are the same, I know that I have similar figures. So that's the first case. And I should say this, not just all interior angles, but I should say all corresponding interior angles are the same. I have a case of similarity. Okay, so that's the first thing that I can do to prove it. Second way to prove similarity is by looking at, here we go, a corresponding side. Okay, so corresponding must have, here we go, same ratio. Now what does that mean? Okay, let me just try to show it to you right here. Let's say I have two triangles like this. One triangle I have this side to be, let's say 6, this is 2, and this is 5, and this is 15, and this right here is 7. Do you see anything here yet? What do you think this side's going to be? Ah, 21. Why must it be 21? Watch what I have. Look at the relationship. 2, how do you get to 6? Times it by 3. 5 times 3 is 15. 7 times 3, 21. And notice that corresponding size, what do I mean by corresponding size? I'm talking about like a scaled down version of your model, right? So think of this as the original model. If this is the side I'm looking at, this is from the big triangle, which side from the small triangle is corresponding to the one that I just marked? The 7. You see it? That's what we call corresponding side. You cannot say, oh yeah, the 5 is corresponding to 21. It's not. They're actually, they're not the same. They're not similar in a sense. They're not corresponding to each other. Okay? And in this case here, 5 is corresponding to 15, and last is 2 is corresponding to 6. You see how the sides are corresponding because they have the same orientation, and if you have to do it side by side comparison, they lean the same way, a certain, and of course the same angles kind of deal. Okay, so, and most importantly, first case I proved by using angles. Second case I'm proving by having the same ratio of corresponding sides. And ratio means what? If you take all the corresponding sides, for example, you see the small triangle here and the big triangle right here. The corresponding side is 2 to 6, right? 2 to 6. If you reduce that, what do you have? 1/3. If you take 7 and 21, reduce that, what do you have? 1/3. And if you take 5 to 15, if you reduce it, what do you have? 1/3. And that's what I'm talking about. Why having the same ratio, base ratio, that is. Isn't ratio basically you can be written as a fraction, right? That's what we're doing. We're comparing small to big, and basically we're just saying that the side from the large triangle is 3 times bigger than the smaller one. And that's a ratio. We're comparing the size. Okay, so that's 2 ways to prove whether something are similar or not. Whether if they have all interior angles that look the same, they are similar automatically. Or if they have sides that have the same ratio, corresponding side having the same ratio, they are, once again, similar as well. It's just like a scaled down version of the exact thing. Think of it as your, the card that I posted up here and have a toy model of it. Every feature looks exactly the same, just smaller, that's all. So you can kind of see that it doesn't matter how big it gets or how small it gets, if they look similar, all the interior angles are automatically the same. Okay? Now we understand the concept of similarity. Let's go back to this first problem here and tell me. Look at Russell and Consuela's proof. Which one here seems kind of like out of ordinary to you? Look at it carefully. First of all, are these 2 triangles similar? Yes. Sorry. Excuse me. Yes. Okay, you're right in a sense because you notice that you have proof that all 3 angles are the same. Corresponding angles are the same. Can you tell me? If I look at angle Y, Which angle is corresponding to angle Y? Okay, angle U. Let's check it to see who got it. Oh, they both got it. Moving on. Look at angle X. Which angle from the bigger triangle is corresponding to angle X? Angle V. So let's check. V should be X, right? That works. But look what happened to Russell. He thought that X is the same thing as T. So apparently, he's not correct, is it? Let's check last one too. Angle T, I should mark that. Angle T is corresponding to what?
Z.
T is to Z. Okay, T is to Z. And apparently, he said Z is to B. So this is incorrect either. So clearly, who's incorrect? Russell. He didn't correspond the angles correctly. Didn't match it up. And notice how this triangle is being flipped, kind of mirrored over. But once again, if you're going to be comparing the angles, you got to make sure that they are corresponding to each other. It's very important. Same thing for the side. Okay, to prove that they are similar. Take a look at our first example here. What I have for you here is just a statement, really. I have this. I said determine whether triangle, I should say, ABC with angle A equals 68 degrees and angle B and C are the same. At least I have my first triangle. Now, what you want to do is just start drawing your first triangle. And how should we label this triangle? How do you want to start?
ABC.
Where should I put the A?
Top.
Does it matter where I put it?
No.
It doesn't. But if you start at the top, then you always start at the top again for the other triangle. So I'm going to start ABC right here. Then I better write. And I'm going to draw another similar triangle. And where should I start my D?
D top.
On top as well. So that's how you do it. And because I'm going clockwise, I also go clockwise on the other one. D, E, F. So I have two triangles. I don't know if they are similar yet. I'm trying to prove it. So let's take a look. It says here that angle A is 68 degrees. Angle B and C are the same. Can we determine what angle B and C's are?
Yeah.
How do we determine that?
Subtract.
Tell me. What would you do? What do you know about a triangle?
180.
Okay, you said that all three angles add up to what?
180.
Okay, so that's the first clue. We know that these two angles are the same. So how do I determine C and B? Yes.
Subtract 180 by 68 and divide it.
Okay, so you say to subtract 68 from 180 to get what? What do you get?
112.
112. 112 degrees. Is this the angle for A? I mean, is the angle for C or B?
No.
Well, what is it?
For both.
Oh, for both. So how do I determine either one?
Divide.
Divided by y2. They're the same, and they're two angles. Good, okay. And so that means I should have what? 56. So that means angle C is 56. So is angle B. All right, so at least I know my interior angles for triangle ABC. Now go over to triangle DEF. It says this. Angle E and angle F, they're both what? 56 degrees. Interesting. So if both of them are 56 degrees, what is angle D has to be?
68.
68. Okay, so if you compare the two and ask this question, are these two similar? What would you say?
Yes.
Why? Based on what? All the corresponding interior angles are the same. And you're right, look. And what do I mean by corresponding? Watch this. Isn't 68 the same angle here? They're corresponding to each other. Angle B is corresponding to angle E, which is also 56. And angle C is corresponding to angle F, which is also 56. That's what I mean by corresponding angles. Interior angles are the same.
Why do you need the marks?
Oh, just to indicate it, that they are corresponding to each other. I know they're the same here for C and B. But I want to make sure that you understand, I make these two marks here for angle A and make these two marks here for angle D because they are corresponding to each other. This is like a scaled down version of it, but they are having the same angle. Okay? It makes more sense when you see this next example here. So they are similar, that's easy enough. Look at this one right here. Clearly you see two triangles. You don't know whether they are similar or not. Let's try to prove whether or not they are similar. We know here that angle here is 87 degrees. This is also 87. This is 43. This is 43. This is 50. interestingly enough, what do you think that one has to be?
50.
Has to be, right? Because if you have two angles that are exactly the same already, then the third one has to be the same as well, by law. Okay? So this is 50 degrees. So all corresponding angles are the same. What can you say about these two triangles? They are similar. Good. And this is the part where I'm going to mark the corresponding angles. Watch this. 50 is corresponding to that angle, right? 87 is corresponding to that angle. 43 is corresponding to this angle right here, 43. For marking, yes. You see how I use 1 mark, 2 mark, 3 mark, because they have all 3 different angles? And at least when I say, oh yeah, I'm comparing this angle to that angle, they are corresponding to each other. Okay, look at the side now. Let's compare the side. Which side is corresponding to which side?
7 to 21 side B.
7 to B. So let's mark that. 7 to B. What else?
15 to A.
15 to A. You see how you use different marking for each side? 15 to A, they're corresponding to each other, so I'm using the same marking. What else?
9 to 27.
9 to 27. So I'm going to use 3 this time. Question so far. And clearly they are similar. All right, so how does that help us in a sense? Well, let's take a look. First of all, on one triangle I have all the sides defined. The other one I have only one side defined. The other twos are missing. So the question now is, can you find out what A and B's are? Okay? Now, how do we start doing something like this? Realize that if they are similar, that means all the corresponding sides must have what? Same ratio. Ratio is, simply put it, it's just a comparison between two things. What are the two things that we have here?
Size.
Look at the figure as a whole. What do we have?
7.
No, look at individual. Look at the whole thing. What do we have up here? Triangles. What kind? We have one small one and one big one, right? And we're trying to compare a small triangle to the big triangle. So, to establish that ratio, all you have to say, am I comparing small to big or big to small? You decide. So I'm saying, okay, for my ratio, I want to compare my small triangle to the big triangle. I just set it up like that, just a basic structure. Okay, are we clear on that? I have two triangles, one small, one big. That's what I'm comparing. A small to the big one. Or if you want to compare big to small, then you write big to small. Doesn't matter. And then now, when you look at it, you look at individual side and determine, well, which two sides are corresponding to each other. In this case, think about this. Let's take a look. Look at size 7. What is it corresponding to?
B.
B. And size 7 comes from what triangle? Small. And small is clearly on the top, right? And the big is on the bottom. So as soon as you establish that, whatever comes from the small triangle, it has to be on the top. Whatever comes from the big triangle goes to the bottom. And because I'm comparing the corresponding side, 7 to B, where do I put the B?
Bottom.
And the 7?
Top.
Question on that? Questions? Okay, next one. I'm comparing 15 to what?
A.
And where do I put the 15?
Top.
And bottom, right? So far, I can't really do anything yet because these two are unknown. But what I realize is this. Oh, wait a minute. Look at the 9. What's the 9 comparing to? 9 to 27. Oh, wait a minute. I have known values. 9 over 27. Can I simplify that?
Yeah.
Yep.
What does it simplify to?
1/3.
1/3. That right here, guys, is your base ratio. As soon as you find your base ratio, you can set up a proportion to solve for any missing value. Because we realize that all similar triangles will have the same ratio, right? Same ratio means I can actually set up the proportion for it. I know that the ratio for each corresponding side is not going to be 1/3. Then all I have to do is set this, each of them equals to 1/3, and solve for it. That's all we're doing. Do you see how it's done so far? I mean, logically, you can certainly do it in your mind. Look, this side, how many times bigger is this side to this side?
3 times.
3 times. Is that what we got? 1, 3, 1 and 3? 3 times, see? This is the big, this is small. It's 3 times bigger than the small. So, I mean, logically, you can determine what B is in your head. What should B be?
21,
21, because it's 3 times bigger. What do you think A should be?
45.
45.
Yeah. But to prove it, watch. I have proportion, I cross multiplied, I got B equals to 21. And over here, once again, cross multiplied, A equals to 45. Do you see how it's done? So, importantly, what you need to establish is having this base ratio right here. I know I kind of went out my way and show you all the corresponding side, what I'm comparing. But you need to have this first, right? You need to establish what we call, what is the base ratio? How many times bigger is the size from the big triangle to the smaller one? And you always want to look for the size that have the values already defined. You see how it's done? Okay? So, there is any questions on that? Alright, let's see if we have that one there. Look at these two triangles. What do you see? Okay, it's 2 and 1, right? Well, can we actually pull one out?
Yes.
Okay, let's pull it out. That means we pull this triangle, smaller triangle, outside. And, let me just draw it out for you here. It will look like this.
We still know it?
Yes.
I thought so.
Yes. Is that correct? And, I'm just going to erase this part because I don't want you to get you confused. I basically just pull out the small triangle inside the inside the other triangle, the big triangle, outside. And clearly now you see triangles. 2 triangles, right? You have a small triangle, you have a big one, and I'm trying to determine, assuming they are similar as well, I want you to go and determine what that side is. X. What is x equals to? Right? So, just like always, you need to start finding your corresponding sides. Which side is corresponding to which side? 5 and x. Good. So I'm going to mark that. 5 and x. What else?
7 and 11.
7 and 11. Notice I'm using different marking as well. Okay, so I got my corresponding size. All good to go. And ask yourself, well, what am I comparing? Big to small or small to big?
Small to big.
Doesn't matter. Doesn't matter if you compare either way?
No.
It doesn't. But if you like to start from small to big, then you just write it first. I'm going to go compare my small to my big triangle. So let's first establish your ratio. Compare ratio. What can I use to compare?
7, 11.
Very good. Where do I put the 7?
On top.
Top.
And 11?
Bottom.
Can I reduce?
Yes. Wait,
No.
No. Fine. Then that's it. This is your base ratio. You got it. Now, let's figure out the rest. What's the next thing I'm going to compare?
5 and x.
Okay, where do I put the x?
Bottom.
Okay. And if I want to solve for it, I set this as a what? How do I solve this now?
Cross.
But before I cross, what do I need to set this to?
Equal.
Yeah, proportion, right? Because I know that they will have the same ratio, so therefore I can set them equal. This ratio will equal to that ratio, therefore I can make them equal, right? And of course, I have fraction on each side. How do I solve?
Cross.
Cross multiply, okay. And I have 7x equals to 55. How do I solve for x? Divided by 7. X is? What's 55 divided by 7? 7 point something? Let's do it once and for all. Sure, let's do it. 7 goes 749 times. 55 minus 49?
6.
6. 7 goes to 60? 8. 56, right? 4. And 0 again. 7 goes into 5. 35. So you get back to 5. Okay, it can go on and on, right? But you can certainly see what's happening, right? So roughly about 7.85. You want to do like that? Or you can leave it as a fraction of 55 over 7. So x is either 7.85 or 55 over 7. Okay, question on that one? What do you think of the? What do you think of this? Is that easy to conceptualize? I hope that this is what's happening when you have two triangles. You've got to make sure they are similar first before you start looking for corresponding sides to find the missing side.